Hello, my name is Katherine Merseth, and I had the wonderful opportunity of speaking with you earlier this year about psychological safety and the development of a strong culture in your schools. Tonight, which is my evening, probably your morning, what I want to do is to take a very brief time to talk about the use of the instructional core and the task. Now, I know that you discussed this material with Elizabeth City, where she helped you understand how important it is, the tasks that we set for children. And what I want to do in this session is to take it a little bit deeper and to talk about math with regard to the task. So let me share my screen and we will begin. What I've titled our session this evening is Developing Rigor in Mathematics Using the Instructional Core. And one of the first things that I want to mention is a frustration, actually, that I have, which is it seems like so many people are so comfortable saying, oh, I was never any good at math. I couldn't do it. I don't have the math gene. I'm not smart in math. And this is very frustrating for me and for my math teacher colleagues, because it's simply not true. Everyone can be good at math. So where does this come from? Well, one of the things that we find is that maths have a very bad reputation because of the way it is taught. And let me share with you this particular example, a piece of research that was done several years ago that put the following question to fourth graders. There are 125 sheep and 5 dogs in a shepherd's flock. How old is the shepherd? Well, most of you would look at that and say, well, that's a silly question. It doesn't have a correct answer. But in fact, the researchers found that 74% of 10-year-olds reported a numerical answer. And they said things like, let's see, 125 plus 5 is 130. Nobody can live that old. 125 minus 5, no, that doesn't work either. 125 divided by 5 is 25. That's it. The shepherd must be 25 years old. So this is the kind of thing that we as teachers have done to children. We have caused them to think that there's always a right answer in mathematics, that most of the success in mathematics comes from memorization and not from understanding. And in fact, it's just simply not the case. So let me show you some examples and some ways to think a little further about how we can contradict this approach. Characteristics of successful math students are those who are willing to take a risk, are those who don't believe that there's always a right answer, that see math as a puzzle and can live with ambiguity. They're not looking for a rule to solve, and they're friendly with numbers. They almost play with numbers. They'll say 8 plus 7 is 15. Now, what if it were 8 plus 8? That's one more, so 15 plus 1. What else? What other number sentences could I make? These are the students who are not afraid of mathematics, who are not fearful of getting the wrong answer. And in fact, there are more math problems where there are not correct answers in the real world than there are those that there are absolutely correct answers. So successful math students understand that it's more about a way of thinking, a way of being. They see maths as a way of asking questions, exploring data, and feeling comfortable not knowing for sure. And a lot of that comfort comes from the teacher, so that if the teacher is conveying a nervousness, a demand for the answer, the child hears that, interprets that, and says, oh, I have to remember it. What is it? Oh, if my memory has failed me, I'm lost. The idea is to present mathematics as an exploration, as a way of looking at ideas and concepts. Now, there's some PISA results, you know about the PISA, that they found that students respond to mathematics and solve them in 3 different ways. One is they use memorization. 2, they relate to other concepts. So they say, well, if it worked this way with another concept that I understand, then maybe it will work this way in this new situation. And the third group are those who do self-monitoring, who are almost have an out of person possibility of looking at themselves and saying, how am I thinking about this? How am I doing? Not surprising, the students who relied on memory are the students who do the worst on a standardized test like PISA. Working with Liz City, and Liz spoke to you about the importance of task and how task is such a simple idea, but a powerful one to help improve the rigor and the level of understanding of students. And so, Liz, you may recall one of her main points to you was that task predicts performance. And so, how do we make sense of that? Well, what I want to show you in this particular presentation is there are 2 ways to think about tasks. One is the actual task that you ask your students to do, but they can have 2 dimensions. They can have one dimension, which is the cognitive demand, which represents the degree of functioning, how much energy your brain has to bring to it. But a second one is the complexity of the content. Is the problem asking you to do just one thing, like multiply 2 numbers together? Or is it asking you to elevate, if you will, and become more complicated, to create, to evaluate, to assess? And I want to show you how this would work. So first, let's start with the one which I think is most memorable to all of us, which is tasks can be low on the cognitive demand scale. They can be knowledge, things you've memorized, comprehension. Think of Bloom's taxonomy, their retrieval and comprehension. And then they can go very high in the cognitive demand dimension, which is synthesis, analysis, and evaluation. And some of you may have seen this new Bloom's taxonomy, where the bottom is the remember. It's the lowest level of the cognitive demand. And as we go up and as we become more complicated, it's becoming understanding, then being able to use what you know, then being able to analyze what you have, evaluate, and create. So here is another view going across, same idea of the cognitive demand from the lower order thinking skills to the higher order thinking skills. So cognitive demand, what are some examples? Low examples would be, what is 8 times 4? That's a straight up memory question. It can be solved if you understand the concept of multiplication, but most times we're asking for memory. What is the Pythagorean theorem? What is the definition of parallel lines? How many degrees in a right angle? These are relatively low. And as we move more complicated, asking our brains to do a little bit more, the examples are a little more involved. When x plus 5 equals 9, what is x? Or 1/2 is the same as how many fourths? Or in the qualitative world, which is a wonderful way to get a handle on math concepts, if it takes 2 lemons and 1 gallon of water to make lemonade, how many lemons would it take to make 2 gallons of lemonade that taste the same? So I'll let you think a little bit about those questions. But as we get higher and move higher up the triangle, Bloom's taxonomy, we do analysis and evaluation and creation. So we can ask students questions like, which is the better buy? 3 peaches for $10 or 4 peaches for $11? Now that takes an application of knowledge about 1 peach would be $3.33, and then how much would 4 peaches be? Similarly, when I ask a question like, which is larger, 2/7 or 4/9, it's not immediately clear. and it's certainly not a memory recall type of a problem. Now on the PISA exam, if any of you are teaching high school, you'll realize that those examples are very high level in terms of analysis, evaluation, and sometimes even creation. So proving, for example, any kind of a proof is more of analysis and evaluation and creation, or draw a picture that shows that a plus b quantity squared is not equal to a squared plus b squared. But there's another dimension, I feel, around mathematics. One is this memory getting harder, applying, using analysis. But the other one is how many different concepts do I have to bring to solve the problem? And tasks can be low in complexity, where they only really require knowledge of one area of mathematics or one concept. And then they can be high, where they are many more connected areas of contact. We can put those two together in this 2x2 matrix, where along the bottom is complexity of content and along the side is the cognitive demand. And let me show you some examples. So here are 4 different questions that relate to the number 4,123. Now in the low area, what numeral is in the tens place? On the cognitive demand side, you just have to remember which place is the tens place. And then moving over to the right, if I ask you to write it in expanded notation, well, now I not only have to understand what 4, 1, 2, 3 means, but I have to bring another conceptual frame, which is that of bases and base 10 to the explanation. Similarly, finding as many numbers as you can that has the same number of tens as 4, 1, 2, 3, or demonstrate how you know that you found all of the examples. Now, how would you classify this task? I'm going to just pause for a minute and let you think about this. So on the equation, what is the value of y when x equals 5? Well, when x equals 5, then I need to know something about substitution. I need to know something about the order of operations, what I do first, what I do second, what rules do I follow there, and then actually completing the task itself. So on this schedule, I would put probably this question somewhere over in the bottom, moving toward the right, because there's a fair amount of knowledge that you need to do this, but there's several other concepts. What does it mean to square? What are the order of operations that I have to bring to this? But we can debate this. There's not necessarily one correct answer. The point is to analyze your tasks. Here's another example from PISA, which is one of my favorites. Pizzeria serves 2 round pizzas, and one is a smaller diameter of 30 centimeters and costs 30 zeds, and the larger one has a diameter of 40 centimeters and 40 zeds. Which pizza is the better deal? Well, you don't have to know any formulas for the area of a circle in order to be able to do this problem, but you do have to bring to bear the concept of unit cost. And therefore, I would classify this task up to the upper right quadrant in our 2x2 matrix. Here is yet another PISA problem, and let me remind you that these problems are expected to be handled by 15-year-olds. And so they give a picture of a water tank, and at the beginning the tank is empty, and then slowly it is filled up with the water at the rate of 1 liter per second. And the task is to graph how the height of the water surface changes over time. And I will leave that, the answers are A, B, C, D, and E. I will leave that for you to ponder. What I want to leave you with is this idea of using the matrix to think of as a tool for instructional improvement. So one way that I've used this is I ask teachers to come together and look at the tasks that they do, that they're offering for their students, and deciding where on the matrix do those tasks fit. Because we certainly want to get away from the lower left-hand corner and generally move toward the upper right-hand corner. But it is a tool that can be used to think carefully about what are you asking students to do. Another one is to look at actual student work and working with teachers around the instruction. If you have the students' work in hand, it is a powerful way to think about how the students are interpreting the tasks and what they think they can do with it. And then finally, we can use this tool for research and for ways of observing and analyzing what is happening in the classroom. Increasing rigor means asking open-ended questions and questions that have no clear answers, as much as that may feel counterintuitive to you in teaching mathematics. They are questions, and increasing rigor are questions that engage the students. They allow them to struggle with questions that are just beyond their current understanding. Not so hard as they would never make any progress, but just a little bit harder than just a straight up application of what the teacher did yesterday. Increasing rigor does not mean making simple problems harder. For example, in a fraction addition problem, if you have 1/3 plus 1/17, that's pretty hard. You know, I've got to think about common denominators and it's not obvious what they are. So rather than trying to make the problems harder, we want to make the problems more interesting. And we want to test their conceptual understanding by asking, what does 1/3 mean? Can you draw a picture? Is 1/3 more or less than 1/5? How do you know? And how would you show in a picture? These are ways that the questioning techniques of teachers in classrooms can increase the exploration of mathematics, not the drive to always get one answer. So to achieve greater rigor, we really need teachers with a sufficiently deep understanding of the core subjects. We need, frankly, longer blocks of time at the secondary level so students can explore and maybe even do some things in an interdisciplinary way. One of my favorite tasks for my students in high school was to assign them an essay question, which they thought was pretty outrageous for a math teacher to do, but nonetheless, I went ahead and did it. And I asked them, if you were 0 and everyone else in the world was a non-zero number, how would you feel? And this really got them thinking about the concept of zero. And I got brilliant essays and very poignant essays. So thinking about interdisciplinary classes, I think, is a way to do this. Engaging with outside partners who actually apply the mathematics and asking the students what they are interested in, I think is yet another way to increase rigor. So finally, what is important to remember? I want you to take away from this brief conversation that maths is not about memorization, but it's about understanding. Secondly, I want you to know that what we ask students to do is what they will be able to do. The third is the quality of the task. What the task itself is asking means everything. So use this matrix to examine the tasks you are asking your students to do. And be sure to ask open-ended questions. Ask, what do you think? Frequently engage your students in the discussion of maths by asking, why do you think this is so? And in that way, engaging students in the actual discussion of mathematics, I think really will enhance what you can do in your classrooms. It's been great talking to you. I hope you find this somewhat helpful, and perhaps we'll chat again. Goodbye.